Oh yes, welcome to part 2 of our analytical geometry video series. Now, like I said in the first part, if you are anywhere between grade 10 and grade 12, or you are rewriting metric, this was specifically tailor-made for your needs. So in this part of the video series, now we are going to be dealing with straight line on a Cartesian plane. So what am I saying to you? I'm saying you should keep your eyes very much peeled and expect that we are going to be dealing with this Cartesian plane where we have our y-axis and our x-axis, and there's going to be a series of straight lines that we are dealing with in that specific Cartesian plane. Ergo, every straight line we are going to be dealing with is a straight line graph, which is why the slide you now see in the screen is of paramount significance when we are stepping into this topic of ours, the quote-unquote analytical geometry. Now, analytical geometry is otherwise referred to as coordinate geometry, right? So in coordinate geometry, this is what we do. We are going to have a series of shapes that are going to be essentially on a Cartesian plane. Now, sometimes the shape can be a kite, sometimes it could be a trapezium, sometimes it can be a rectangle, a parallelogram, or it can be any form of a triangle that is on a Cartesian plane, or a combination of any of the shapes that we studied in the first part of this video series for analytical geometry. Right? So with that in mind, that now says to us we have to be very well versed with our story of our analysis of straight line functions. So let me just take a few minutes to remind you of what our story is when dealing with straight line functions. So everything when dealing with a straight line function starts with the standard form. Our standard form can come in the form of y is equals to mx plus c like we have here, or it can come in the form where the standard form is reduced to an equation of a line like so. Now, what I want you to take away for yourself is this m in here and this m in here. You see they are both yellows. They both have the same color. It's still the same thing. It's still the same gradient. Meaning this m in here, don't let this m in here deceive you. This m in here is friends with these ones. Actually, they are identical twins. They are identical twins, just that this m is talking is referring to a different aspect of this topic that I will touch on in a short brief moment. For the interim, in this notation in here, the purple parts y1 and x1 are the coordinates of a point along the straight line. So that's that. Y is the subject of the formula, the gradient is the slope or the steepness. Now, likewise, when this gradient of ours is positive, when the gradient is positive, we are going to have a graph that is always, or a line that is always increasing from left to right, as we have in this sketch in here, and vice versa. When this gradient of ours is below 0 or less than 0, ergo negative, we are going to have a graph that is decreasing like this one in here. So without any further ado, there are two ways to calculate the gradient. One is where we are using this formula, and the other is where we are using this formula in here. In order for us to use this formula in here, we need 2 points. You can see that these are the coordinates of the first point. This inputs in here into the formula are the coordinates of the second point. Or we can use this approach in here to calculate the gradient of a line where we are using the angle of inclination. Now, some of you are wondering, this guy is talking a lot of English. What on earth is the angle of inclination? So the story still remains the same. When the gradient is positive, we have a line that is increasing from left to right, like we have in this sketching here. When the gradient is negative or less than 0, we have a line that is decreasing from left to right in here. So what then is the angle of inclination? The angle of inclination is nothing more than the angle between the x-axis. You can see the line I'm now drawing in here is our x-axis and the graph. So the angle between the x-axis and the graph, that's our angle of inclination. That's what angle of inclination is. In this second graph, we can see that, oh, this horizontal line in here is our x-axis. So our angle of inclination is then this theta in here. Now you may be wondering, but we have another theta there at the bottom, and then we've also got another theta here at the bottom, at the aids. What about those thetas? What's happening there? Well, they are still angles of inclination. How so? Because they are not on the x-axis. They are angle of inclinations because there's this dotted line. This dotted line is parallel to the x-axis. This dotted line is drawn parallel to the x-axis. This dotted line is parallel to the x-axis. So, seeing that this dotted line is parallel to the x-axis, it means that this line and the x-axis have the same gradient. Now, seeing as this equation where m is equal to tan theta seeks to calculate the gradient. If two lines have equal gradients, it means the angles between those two lines and the graph are gonna be equal. So seeing as the one line is the x-axis and the other is the projected line that is parallel to the x-axis, they are both angles of inclination. We will be using this strategy to solve those graphs or shapes on a Cartesian plane at a later stage. The same thing applies in here. So I'm just going to go at it a bit slower for those of you that didn't follow along. We've got this dotted line. This dotted line is drawn parallel to the x-axis, meaning the gradient of this dotted line is the same gradient of the x-axis, of which the gradient of the x-axis is 0, meaning the gradient here is also 0. So the angle of inclination is the angle between the line where m is equals to 0 and the graph itself. That is our angle of inclination. So we are always looking for the angle between the line. This dotted line is an angle line where m is equals to 0. Just like this dotted line in here is also the line where m, or the gradient of this line, is equals to 0. So the angle of inclination, I say again, is the angle between the x-axis and the line, the graph, or the angle between the line where m is equals to 0 and the graph itself. That's it about the angle of inclination. From 8 minutes 30 seconds going forward, I am now moving on. We are still going to talk about the angle between the x-axis and the graph. In this case, this is this angle in here. This is the angle between the x-axis and the graph. This is our angle of inclination. Now, what this illustration we have in the first scenario here, in scenario A, we have a gradient, an angle that is slightly higher, meaning the higher the angle, the higher or the bigger the angle, the greater the gradient. When in this second scenario here, we have angle alpha, which is smaller than theta there, so it will have a smaller gradient, seeing as it is much steeper, right? So that is to say, when the slope of the graph changes, or the slope of the line changes, the angle between the x-axis also and the graph also changes, meaning the angle between the line where x is m, the gradient is equal to 0, and the graph will also change. That's that. Now we also have something else in here. In this graph, we have a line that is drawn parallel to the x-axis. We have a line that is drawn parallel to the x-axis. Now, Pardon me for the technical glitch. I was saying we have the x-axis in here, and then we've got another line in here. Now this line that we have in here and the x-axis are parallel. Now the gradient of the x-axis is always equals to 0. The gradient of the x-axis is always equals to 0. So any line that is parallel to the x-axis has a gradient of equal to 0. In a nutshell, I'm saying any two lines that are parallel to each other, they have equal gradients. That's what I said to you. Moving on. On the second scenario here, on the left, we have the y-axis. Now the y-axis is parallel to this vertical line in here. The gradient of the y-axis is always undefined, meaning the gradient of any vertical line or the gradient of any line that is parallel to the y-axis is always what? Undefined. I say again, the gradient of parallel lines are equal, which then brings us to our next slide. Our next slide just reminds or highlights what I was saying. We have line AB being parallel to line CD in here. Now, seeing as line AB and line CD are parallel, these two lines are going to have equal gradients, meaning the gradient of AB is going to be equal to the gradient of CD. Simple enough, ne? When two lines are parallel, their gradients are equal. Now, what of now perpendicular lines? The lines where the angles, the angle between them is 90 degrees. The angle between them is 90 degrees, like so. The angle is 90 degrees between the two lines. When the two lines are perpendicular, like line AB and line CD are perpendicular in here, the gradients of perpendicular lines, when we multiply them, they give us what? -1. To paraphrase, the products of the gradients of perpendicular lines give us what? -1. When we multiply the gradients of perpendicular lines, we get -1. That's what I want you to take away. Any inputs or questions? This has been a rather long video at this point in time, so I'm just gonna go ahead and summarize a few pointers that I would like you to remember from this. That is, when two lines are parallel, their gradients are gonna be equal. When two lines are perpendicular, the products of their gradients are gonna give us -1. When a horizontal line, meaning a line that is parallel to the x-axis, is gonna have the gradient of 0. The x-axis itself has a gradient of 0. A vertical line, meaning a line that has a gradient that is undefined, is a line that is parallel to the y-axis. The y-axis itself has a gradient that is undefined. Now, that is it for this video series. I want you to now take this example and just do a practice quiz. It's a 3-minute quiz that should just give you a brief revision into the calculations of gradients and stuff like that. Now, in the next part of the video series, I'm gonna be rolling things up. We are gonna now look at the first point in this. Using our calculations, we are going to be using the distance and midpoint formulas like so, and so working out problems of various examples. So before I close up the video, I just want you to introduce you into the distance and the midpoint. Now, we can have multiple points on a graph. Let's say we have the first point in here, the second point in here, and then the third point in here. So we have point A, we have point B, and then we have point C in the middle. Now, if point C is the center of AB, meaning AC being equal to AB, that makes point C the midpoint. Whenever we are looking for or to calculate the midpoint between any 2 points. So the midpoint of AB in this case, the midpoint of AB would be the x-coordinated B plus the x-coordinated A divided by 2 as per this formula. Then we'll go to semicolon, and then you go ahead to say the y-coordinated B plus the y-coordinated A divided by 2. That's how you would get the coordinates of a midpoint on any given straight line. Doesn't matter if the gradient, how the straight line is sloping, so long as it's a straight line and you want to calculate the halfway point between any 2 points whose coordinates you know. That's how you can use the midpoint formula, right? And then we've got the distance. We can calculate, if we know the coordinates of A, we know the coordinates of B and the coordinates of C. We can try to calculate the coordinates or the distance between the 2 points we know. If we know the coordinates of A and B, then we can try to calculate the distance of AC. And by the same token, if you know the distance between the coordinates of A and B and C, if we know the coordinates of B and C, we can use that distance formula to calculate the distance of BC. By the same token, if we know the distance or the coordinates of A and B, we can use the distance formula to calculate the distance of what? AB. Right, that's the second part, introduction to analytical geometry. Thank you very much, my fellow FETs, my fellow mathematicians. Now, going forward, we are going to be getting into practice examples. So get your pens out, be ready to start doing the things. I just want to leave you with a very final point before we go ahead and close this video. That's collinear points. That is to say, if you know, let's say you know the gradient of AB, you already know the gradient of AB, you know M of AB. Seeing as AB is the same straight line as AC, that simply means that the gradient of the AB I know is going to be equals to the gradient of what? You guessed it, it's going to be equals to the gradient of AC. That is to say, as long as we are on the same straight line, the gradient is going to remain the same all throughout. It doesn't matter that if you are at this point A on the straight line, or you are at some point in here, some point in here, or you are at point B, or you are at point C, or some point in between B and C. So long as it is the same straight line, it's collinear points. Collinear points have what? Equal gradients. So in collinear points, we have equal gradients. And if the AB is equal to BC, then it means the distance of AB plus the distance of BC is going to give us the length of what? AC. That's what this part in here is delineating. Now, my fellow grade 12s, thank you. My fellow grade 11s, thank you. My fellow grade 10s, thank you. Why am I thanking all of you? That is because this is how all you need to grasp in as far as the theoretical or the basic concepts to analytical geometry are concerned. With the exception of the grade 12s, that's a different conversation we are going to have by ourselves, away from all the prying eyes. So thank you very much. Let's see each other on the next video and see the tutorial that I will be sharing with you soon. Stay tuned. See you next time. Peace.